Artificial intelligence. No current technology is more misunderstood, yet met with an abundance of excitement and genuine fear in today's economy. The continued enhancement of AI evokes images of dystopian futuristic societies where humans interact with machines on a daily basis, making our lives impossibly simplistic and yet painstakingly soulless and robotic as a trade-off. One thing is for certain. The genie is out of the bottle and AI is here to stay, despite its ethical and technological concerns. Instead of living in a state of blissful ignorance and naivety towards this newfound scientific paradigm, why not explore the world of AI together to become a subject matter expert and acquire more knowledge than 99% of your peers by the end of this video? If we cannot block the advent of future AI innovation, our insights and understanding on AI can at least guide artificial intelligence in the right altruistic direction to minimize the risk of corruption and primarily capitalistic-driven reasonings towards its advancement. Today's video will cover the definition of AI and its various categories and the hardware behind the technology. Artificial intelligence is defined as machine intelligence that mimics a human mind's problem-solving and decision-making capabilities to perform various tasks. AI has been broadly defined as having three types: narrow AI, artificial general intelligence, and artificial supraintelligence. All AI types use machine learning, deep learning, and neural networks to evolve to higher levels. And irrespective of the type of AI mentioned above, AI typically has three basic abilities. One is to perceive the surrounding environment. Two is to detect the patterns in the environment. And three is to learn from these patterns and update understanding for future decisions. Of the three types of AI, let's first begin with narrow AI, which is an application or task-specific AI programmed to perform singular tasks such as facial recognition, speech recognition, or even driving a car. Narrow AI simulates human behavior based on a limited set of parameters, constraints, and context. Next up is artificial general intelligence, also referred to as strong AI or deep AI. AGI uses a theory-of-mind AI framework to recognize other intelligent systems' emotions, beliefs, and thought processes, allowing machines to truly understand all human aspects, rather than only replicating or simulating the human mind. Although AGI hasn't been realized yet, it has drawn the attention of top tech companies such as Microsoft, which invested $1 billion in AGI through the venture OpenAI. Lastly is artificial supraintelligence, which is a type of AI that surpasses human intelligence and can perform any task better than a human. Although the technology remains a hypothetical, ASI systems would not only understand human sentiments and experiences, but also evoke emotions, beliefs, and desires of their own similar to humans. As a result, this ASI system can think, solve puzzles, make judgments, and take decisions independently. Now that we've covered the detailed description of AI and its three distinct categories, it's important to discern the difference between hardware and software. Hardware refers to the physical and visible components of the system, whereas software, on the other hand, refers to a set of instructions which enable the hardware to perform a specific set of tasks. Examples of AI hardware include AI chips, semiconductors, and supercomputers. And although I will cover software in more detail in another video, examples of AI software include machine learning, deep learning, neural networks, natural language processing, large language models, generative AI, and agentic AI. From an AI hardware perspective, first let's begin with AI chips, as they are designed to handle the uniquely complex computational requirements of AI algorithms quickly and efficiently. In general, a chip refers to a microchip, which is an integrated circuit unit that has been manufactured at a microscopic scale using semiconductor material. Components like transistors, which are tiny switches that control the flow of electrical current within a circuit, are etched into this material to power computing functions, such as memory and logic. While memory chips manage data storage and retrieval, logic chips serve as the brains behind the operation that processes the data. AI chips largely work on the logic side, handling the intensive data processing needs of AI workloads. To achieve this, they tend to incorporate a large amount of faster, smaller, and more efficient transistors. This design allows them to perform more computations per unit of energy, resulting in faster processing speeds and lower energy consumption compared to chips with larger and fewer transistors. AI chips also feature unique capabilities that dramatically accelerate the computations required by AI algorithms. This includes parallel processing, which is crucial in artificial intelligence, as it allows multiple tasks and calculations to be performed simultaneously, enabling quicker and more efficient handling of complex computations. AI chips also tend to be able to perform AI-related tasks like image recognition and natural language processing with more accuracy than regular chips. Their purpose is to perform intricate calculations involved in AI algorithms with precision, reducing the likelihood of errors. Importantly, unlike general-purpose chips, some AI chips can be customized to meet the requirements of specific AI models or applications, allowing the hardware to adapt to different tasks. These customizations include fine-tuning certain parameters, which are variables within a trained model, and optimizing the chip's architecture for specific AI workloads. This flexibility is essential to the advancement of AI, as it enables developers to tailor the hardware to their unique needs, accommodating variations in algorithms, data types, and computational requirements. As AI has become more sophisticated, the need for higher processing power, speed, and efficiency in computers has also grown, and AI chips are essential for meeting this demand. There are 5 different categories of AI chips, which include central processing units, or CPUs, graphics processing units, or GPUs, field programmable gate arrays, or FPGAs, application-specific integrated circuits, or ASICs, and neural processing units, or NPUs. First, central processing units can be used for simple AI tasks, but they are becoming less and less useful as the industry advances. Second, GPUs are most often used in the training of AI models, as GPUs were originally developed for applications that require high graphics performance, like running video games or rendering video sequences. These general-purpose chips are typically built to perform parallel processing tasks. Because AI model training is so computationally intensive, companies connect several GPUs together so they can all train an AI system synchronously. Third, FPGAs are useful in the application of AI models because they can be reprogrammed on the fly, meaning they are hyper-specialized. In other words, FPGAs are highly efficient at a variety of different tasks, particularly those related to image and video processing. Fourth, ASICs are accelerator chips designed for a very specific use, in this case, artificial intelligence. They are custom-built to support specific applications, and ASICs offer similar computing ability to the FPGAs, but they cannot be reprogrammed. Because their circuitry has been optimized for one specific task, they often offer superior performance compared to general-purpose processors or even other AI chips. And fifth, NPUs are modern add-ons that enable CPUs to handle AI workloads and are similar to GPUs, except they're designed with the more specific purpose of building deep learning models and neural networks. As a result, NPUs excel at processing massive volumes of data to perform a range of advanced AI tasks like object detection, speech recognition, and video editing. Because of their capabilities, NPUs often outperform GPUs when it comes to AI processes. Shifting gears, there are 4 main challenges that AI chip makers face today, which include monopoly concerns, supply chain bottlenecks, fragile geopolitical constraints, and computational constraints. At the moment, NVIDIA is a top supplier of AI hardware and software, controlling about 80% of the global market share in GPUs. But this dominance hasn't come without controversy. Alongside Microsoft and OpenAI, NVIDIA has come under scrutiny for potentially violating US antitrust laws. There's also a large number of technology players hard at work to try to catch up with NVIDIA's AI chip lead. Amazon, for example, came out with its new Trainium 2 chip, claiming that it achieves the same performance as NVIDIA's H100 chip at a fraction of the cost. OpenAI is also aiming to finalize its chip design in 2025 to improve its leverage in negotiations with other chip manufacturers. The OpenAI chip will be manufactured by Taiwan Semiconductor Manufacturing Corporation, or TSMC, using the same 3nm process as NVIDIA's Blackwell architecture. From a supply chain perspective, TSMC makes roughly 90% of the world's advanced chips, powering everything from Apple's iPhones to Tesla's electric vehicles. It is also the sole manufacturer of NVIDIA's powerful H100 and A100 processors, which power the majority of AI data centers. TSMC's control over the market has created severe bottlenecks in the global supply chain. The company has limited production capacity and resources, which hinders its ability to meet escalating demands for AI chips. These supply chain shortages won't last forever, though, as TSMC's subsidiary, Japan Advanced Semiconductor Manufacturing, or JASM, is constructing a factory in Kumamoto that is expected to be at full production by the end of 2024. TSMC is also building 2 state-of-the-art plants in Arizona, the first of which is set to begin chip production in 2025. In the meantime, prominent AI makers like Microsoft, Google, and Amazon are designing their own custom AI chips to reduce their reliance on NVIDIA. There have also been wider attempts to counter NVIDIA's dominance, spearheaded by a consortium of companies called the UXL Foundation that developed an open-source alternative to NVIDIA's CUDA platform and Intel, who directly challenged NVIDIA with its latest Gaudi 3 chip. From a geopolitical perspective, Taiwan, which plays a central role in the global supply of AI chips, is viewed by China as a rogue province as opposed to an independent nation. Because of this, some analysts believe a Chinese invasion could occur within a decade. This would affect TSMC's ability to manufacture AI chips and put the entire AI industry in jeopardy. Additionally, amid tensions between the United States and China, former President Joe Biden rolled out a sweeping set of export controls in 2022 that dramatically limited China's access to AI chips, chip-making equipment, and chip design software, much of which is controlled by US companies like NVIDIA. Although companies like Intel can still introduce new AI chips in China, they must limit the performance of these chips. China has also sought homegrown alternatives to NVIDIA like Huawei, but software bugs have frustrated these efforts. As the US works to limit China's access to AI hardware, it is also taking steps to reduce its own reliance on chip fabrication facilities in East Asia. In addition to facilitating the 2 TSMC plants in Arizona, the government has secured a third TSMC site in Phoenix through the CHIPS and Science Act, and also set aside more than $52 billion in federal funding and incentives to support US semiconductor manufacturing, research, and development. And lastly, from a computational constraints perspective, developers are creating bigger and more powerful models, driving up computational demands, which is pushing the finite computational resources of AI chips to the limit. The amount of chips that you need to scale a state-of-the-art AI system is growing by about 4 times every year. Meanwhile, the algorithmic efficiency of chips, or the ability to do more with fewer chips, is growing by 2 times every year, thus outstripping what the industry is currently able to provide. Instead of simply throwing more chips at the problem, companies are rushing to figure out ways to improve AI hardware itself. One key area of interest is in memory computing, which eliminates the separation between where the data is stored, or the memory, and where the data is processed, or the logic, in order to speed things up. Additionally, AI chip designers like NVIDIA and AMD have started incorporating AI algorithms to improve hardware performance and the fabrication process. With the AI section now covered, let's shift our focus to semiconductors and the materials used to create them. As mentioned before, a microchip is an integrated circuit unit that has been manufactured at a microscopic scale using semiconductor material. Semiconductors control the flow of electrical currents within electronic devices and are present in all types of electronics, including smartphones, computers, automotives, energy storage, medical devices, lighting, military, and aerospace applications. Alarmingly, semiconductors are incredibly mineral intensive, with 4 indispensable minerals that include gallium, germanium, palladium, and silicon, which all face significant supply chain risks due to dependence on Russia and China. Current government funding and tax incentives are inadequate to address this issue. For example, the CHIPS and Science Act of 2022 was designed to boost semiconductor manufacturing, but does not include any support for the related mineral inputs. The CHIPS Act provided over $280 billion for advanced chip manufacturing, packaging, and workforce development, thus focusing almost entirely on onshoring downstream capabilities. Without sufficient raw materials, semiconductor and microchip production remains vulnerable to geopolitical tensions, as evidenced when China imposed export restrictions on gallium and germanium in 2023. China currently accounts for 98% of the world's refined gallium and 68% of the world's germanium production. The United States, meanwhile, produces no gallium and less than 2% of the world's refined germanium. The US Geological Survey estimated that just a 30% supply disruption of gallium could cause a $602 billion decline in US economic output, equivalent to 2.1% of gross domestic product, posing a significant economic threat. As mentioned before, the 4 key materials in semiconductor production involve gallium, germanium, palladium, and silicon, which we will now examine in more detail. Firstly, gallium is the key to unlocking higher power and higher frequency electronics. Yet the mineral is also the semiconductor mineral with the highest supply chain vulnerability. Used to produce GaN and GaAs high-performing chips, gallium offers higher speed, lower resistance, and lower production costs when compared to alternatives. The difficulty in diversifying gallium sources centers on the mineral's availability, as it is exceedingly rare in the Earth's crust, less than 19 parts per million or ppm, and is sourced only as a byproduct of bauxite mining. The United States has small bauxite reserves, just 20 million metric tons, and minimal mining activity. Guinea, however, has the world's largest bauxite reserves at 7.4 billion metric tons, followed by Australia at 5.1 billion and Brazil at 2.7 billion. Most of these exports, however, went to China for refining, For example, 81.5% of Guinea's bauxite exports went to China, as did 97% of Australia's and 100% of Indonesia. If the United States seeks to increase its bauxite imports from non-Chinese sources, the private sector will need to invest in mineral refining infrastructure in bauxite-rich allied nations and secure offtake agreements with Western mining companies. Next up is germanium, which is a key material for high-speed transistors due to its high electron mobility. No alternatives to germanium exist without significant performance losses. Germanium is sourced as a byproduct of the processing of zinc ores, and it does not occur as a natural metal. The Earth's crust is only 1.5 ppm germanium, making the mineral one of the rarest metals on the periodic table. Countries with the greatest zinc reserves aside from China include Australia, Peru, and Mexico. As the world-leading producer of refined germanium, China accounts for about 60% of global supply. Since imposing export restrictions last year, germanium prices have climbed over 70% to $2,280 per kilogram. Germanium needs significant refining to become more suitable material for semiconductors, and germanium refining infrastructure is currently dominated by China. Companies in the United States face significant hurdles in justifying investment in new refining capacity for germanium. Germanium refining is particularly expensive as the metals need to reach purity levels of 99.999%, while China manages to keep production costs low through reduced environmental and social safeguards. Manufacturers outside of China have not been able to compete. Without the kind of government subsidies Chinese competitors have, US companies will not be competitive in the face of higher labor and power costs, necessitating financial incentives to reduce the cost of doing business. The third raw material critical in semiconductor manufacturing is palladium. Palladium is used in the metal connections attaching chips to circuit boards, and palladium plating is used on semiconductors to ensure longevity and reliability. As semiconductors advance and chips become increasingly compact, the risk of oxidation and deterioration arises. Palladium's durability and corrosion and oxidation resistance make it a crucial protective shield on chips to ensure their sustained performance. The United States produces just 5% of the world's palladium, whereas Russia holds the world's largest palladium reserves and produces over 40% of the world's palladium. Compounding matters, the World Platinum Investment Council predicted a 1.28 million ounce palladium deficit in 2024, equivalent to over 1/3 of Russia's total production in 2022. These deficits are largely the result of supply issues as mine producers restructure in response to a period of suppressed prices. Now, South Africa holds the world's second largest reserves of palladium, contributing 34% of the world's production. However, the industry faces several challenges in South Africa, including rising production costs, energy and transport infrastructure failures, lack of permitting, labor disputes, and declining ore grades. As current palladium prices make domestic mining operations untenable, the United States needs to be incentivizing investment in countries such as South Africa, where operation costs will be more competitive with Russia, and therefore projects will be more likely to succeed. Lastly is silicon, which is the most important mineral for semiconductor manufacturing and is used to make silicon wafers, the largest portion of the semiconductor materials market. Although Japan and South Korea perform the majority of global silicon wafer manufacturing, China accounts for 79% of global raw silicon production and 75% of the ultra-high purity polysilicon needed for semiconductors, demonstrating the need for polysilicon manufacturing in allied countries in order to diversify silicon sourcing and reduce potential supply chain disruptions. Silicon is the second most common element in the Earth's crust and is mined in open pits as silica sand. However, silicon is bound to oxygen, alumina, and magnesium, so it has to undergo extensive refining to extract silicon metal and produce high-purity polysilicon. In the early 2000s, an oligopoly of 7 companies known as the Seven Sisters, and all located in the United States, Japan, and Germany, dominated the polysilicon market. Today, 6 companies dominate the global polysilicon supply. 5 of those 6 companies are Chinese-owned. As a strategy moving forwards, building a resilient domestic semiconductor industry will require not only incentives and subsidies in downstream manufacturing, but also support to develop mining and refining capabilities in allied countries. US policymakers have so far done little to incentivize diversification of these supply chains by the private sector. The semiconductor industry needs a set of tax incentives and funding programs to spur the private sector, just as the IRA spurred investment in EV mineral supply chains. To address supply chain vulnerabilities, policymakers should prioritize 1. Creating an investment tax credit for processing and refining projects. 2. Opening national laboratories focused on semiconductor mineral research and development. 3. Expanding eligibility for DPA Title III grants, and 4. Offering direct subsidies to encourage offtake agreements with Western companies. Now that we've covered AI chips and semiconductor production, the last piece of the hardware puzzle are supercomputers, which we will discuss next. A supercomputer is a type of computer with a high level of performance as compared to a general-purpose computer. The performance of a supercomputer is commonly measured in floating point operations per second, or flops, instead of million instructions per second, or MIPS. Since 2022, supercomputers have existed which can perform over 10 to the power of 18 flops, so-called exascale supercomputers. Supercomputers play an important role in the field of computational science and are used for a wide range of computationally intensive tasks in various fields, including quantum mechanics, weather forecasting, climate research, oil and gas exploration, molecular modeling, which involves the computing of structures and properties of chemical compounds, biological macromolecules, polymers and crystals, as well as physical simulations, such as simulations of the early movements of the universe, airplane and spacecraft aerodynamics, and the detonation of nuclear weapons and nuclear fission. And lastly, cryptanalysis, which is used to breach cryptographic security systems and gain access to the contents of encrypted messages, even if the cryptographic key is unknown. Supercomputers were first introduced in the 1960s, and the US has long been the leader in the supercomputer field. The US currently has 5 of the top 10 supercomputers, with Italy having 2 and Japan, Finland, and Switzerland having 1 each. As of November 2024, Lawrence Livermore National Laboratory's El Capitan is the world's fastest supercomputer. Systems with a massive number of processors generally take one of 2 paths. In the grid computing approach, the processing power of many computers, organized as distributed diverse administrative domains, is opportunistically used whenever a computer is available. In another approach, many processors are used in proximity to each other, for example, in a computer cluster. In such a centralized, massively parallel system, the speed and flexibility of the interconnect becomes very important, and modern supercomputers have used various approaches, ranging from enhanced InfiniBand systems to 3-dimensional torus interconnects. Throughout the decades, the management of heat density has remained a key issue for most centralized supercomputers. The large amount of heat generated by a system may also have other effects, such as reducing the lifetime of other system components. There have been diverse approaches to heat management, from pumping floor inert through the system to a hybrid liquid air cooling system or air cooling with normal air conditioning temperatures. A typical supercomputer consumes large amounts of electrical power, almost all of which is converted into heat requiring cooling. For example, the supercomputer Tianhe 1A consumes 4.04 megawatts of electricity, and the cost to power and cool the system can be significant, as 4 megawatts at 10 cents per kilowatt is $400 an hour, or about $3.5 million per year. Supercomputers generally aim for the maximum in capability computing rather than capacity computing. Capability computing is typically thought of as the maximum computing power to solve a single large problem in the shortest amount of time. Often, a capability system is to solve a problem of size or complexity that no other computer can. For example, a very complex weather simulation application. Capacity computing, in contrast, is typically thought of as using efficient, cost-effective computing power to solve a few somewhat large problems or many small problems. Architectures that lend themselves to supporting many users for routine everyday tasks may have a lot of capacity, but are not typically considered supercomputers given that they do not solve a single, very complex problem. 2 examples of complex problems come from first, the IBM Blue Gene P computer, which has been used to stimulate a number of artificial neurons equivalent to approximately 1% of a human cerebral cortex, containing 1.6 billion neurons with approximately 9 trillion connections. Second, in early 2022, at the height of the COVID-19 pandemic, supercomputers used different simulations to find compounds that could potentially stop the spread. These computers ran for tens of hours using multiple parallel running CPUs to model different processes. When the Top 500 list, a ranking of the 500 most powerful non-distributed computer systems in the world, was first published in 1993, the thinking machine at the Los Alamos National Laboratory in California held the world's greatest processing power. With its 1,024 processors, it could perform an average of 59.7 billion complex mathematical calculations per second, a measure known as gigaflops. Today, the most powerful supercomputer can perform 1,194,000 trillion of the same operations per second, or 1,194 petaflops. In 2022, it was announced that Frontier had become the first supercomputer in the world to reach exascale. Frontier is currently being used by 1,580 researchers across 240 active projects, including at startups and Fortune 500 companies. Teams are working on computational problems in a wide array of areas, from nuclear physics and climate science to mechanical engineering and drug discovery. By using supercomputers like Frontier for modeling, simulation, visualization, and large-scale data analysis, researchers are able to accelerate innovation while lowering its risk, resulting in lower cost, faster time to market, and increased revenue. Supercomputers have been developed in a number of emerging markets, including Thailand, Brazil, and Saudi Arabia. However, the key for supercomputers to truly drive economic growth when it comes to AI specifically is not to continuously build faster and faster supercomputers. Rather, it is to set up many smaller clusters, because every Fortune 500 company is going to require its own supercomputer at some point. Let's now discuss the companies that have chosen to build their own supercomputers. Tesla, for example, has chosen to build its own supercomputer called Dojo, which will be used to improve software in its fleet of autonomous vehicles. In July 2023, Tesla CEO Elon Musk said the company would commit more than $1 billion to the Dojo project up to the end of 2024. OpenAI is planning to build a $100 billion data center and supercomputer called Stargate for creating state-of-the-art AI that is far more capable than today's technology. Stargate could be running by 2028 and require as much as 5 gigawatts of power. Microsoft is also deploying supercomputers outside of its partnership with OpenAI, launching the equivalent of 561 petaflop Eagle supercomputers every month. Google's future supercomputer plans are based on the performance of Willow, the company's latest quantum chip. Meta recently announced 2 24K GPU clusters built on top of Grand Teton, OpenRack, and PyTorch. By the end of 2024, the company planned to have 350,000 of NVIDIA's H100 GPUs as part of a portfolio that will feature compute power equivalent to nearly 600,000 H100s. This past November, Amazon announced it was deepening its collaboration with Anthropic, which will use AWS Trainium and Inferentia chips to train and deploy its future foundation model. Amazon and Anthropic also previously announced a strategic collaboration, which included Anthropic naming Amazon Web Services, or AWS, its primary cloud provider, and Amazon making a $4 billion investment in Anthropic. NVIDIA recently announced a new compact generative AI supercomputer, the Jetson Orin Nano. This technology delivers a 1.7-time increase in generative AI inference performance, a 70% increase in performance, and a 50% increase in memory bandwidth compared with its predecessor. Lastly, IBM's next-generation quantum computer architecture quantum processor will be deployed at the Riken Center for Computational Science in Kobe, Japan. In addition to the project, IBM will also work to develop the software stack dedicated to generating and executing integrated quantum classical workflows. These new capabilities will be geared towards delivering improvements in algorithm quality and execution times. Overall, today we covered the core definition of AI, the different categories of AI, which include narrow AI, artificial general intelligence, and artificial superintelligence, and finally the various hardware components powering AI, which involve AI chips, semiconductor manufacturing, and supercomputers. In the next video, we will discuss the background history of artificial intelligence, the biggest AI companies in the market today, and the software that fuels AI's incredible achievements. Until next time, thanks for watching, and please like and subscribe for more great content.